Welcome to the deep dive. We got our hands on quite a document this time, the Codeco D10 deliverable. You sent it in, and yeah, we're diving straight into the architecture of this major European project.
Yeah, this is a big one. Codeco.
Codeco, cognitive, decentralized, edge cloud orchestration. I mean, it sounds complex, and, well, it is. This engineering doc basically lays out the open source plan for managing, well, the mess that is modern infrastructure, right?
That's a good way to put it, the mess. The mission here is pretty critical. See, applications today, especially the ones needing real-time responses, they don't just sit nicely in a data center. They're spread all over the place. Cloud, edge, IoT devices, what they call the CEI continuum.
Right, the continuum.
And the tools we have now, mostly based on standard Kubernetes K8s, they really struggle with that sprawl. They just don't have the full picture, the context.
So Codeco comes in.
How?
It's designed as a pluggable framework, an extension for K8s, built specifically to handle this dispersed environment. Okay, and I think the biggest thing for you listening to grab onto right away is this. Codeco isn't just looking at CPU and memory anymore. That's the old way.
Exactly. They're shifting to a whole different strategy. Think data compute network orchestration. All three are treated as, equally vital resources to manage.
That integrated approach.
Yeah.
It makes sense. The document keeps hammering this point. Applications need to run anywhere and everywhere, so they have to be super lightweight, really portable, and mobile.
Precisely. And it's not just about squeezing big apps onto small devices. It's about processing vast amounts of data very quickly, often in, let's say, unstable network conditions. And crucially, supporting real-time decision-making.
Like self-driving cars or maybe factory robots.
Yeah, things like that. Industrial IoT. If that decision doesn't happen instantly, the data is useless. Or worse, something goes wrong.
Okay, so it builds on K8s, but you mentioned mobility. How does it handle that differently? K8s is great at replication, right? Making copies.
Right. K8 spins up a copy, replica pod, somewhere else. But the original, it might still be running, using resources, holding on to state until it eventually gets cleaned up. That's not ideal for true mobility.
So what does Codeco do?
It specifically supports offloading. Think of it more like relocation. Imagine a microservice on a drone flying between network zones. Codeco manages the handoff. It tears down the workload and its state in the old spot and cleanly recreates it in the new one.
So it's a proper move, not just a copy. It deletes the old one as part of the process.
Exactly. A genuine handoff and teardown. Yeah. That's key when the node itself is moving, like that drone example. You can't have two versions potentially conflicting.
Makes sense. And who's actually using this system? The document mentions specific roles.
Yeah, two main user types. You've got the application developer, the DEV. They're the ones saying, here's what my app needs to run well.
Okay, defining requirements.
And then there's the infrastructure manager, the MGR. They handle setting up the clusters, managing the actual hardware and network, the runtime environment. Both of them have a say in, the optimization goals.
Got it. Okay, let's shift from the foundations to the actual mechanics. Yeah. How does it pull off this data compute network integration? You said there are components.
5 main pillars, yeah. Think of them working together. It starts with the user interface, which is automated configuration management, or ACM.
ACM, the entry point.
Exactly. The single entry point for both the dev and the manager. The dev puts their requirements, quality of service, quality of experience into a YAML file. They call it the Codeco application model, or CAM.
So a config file, basically, the CAM.
Pretty much. And that CAM becomes the roadmap. ACM's job is just to make sure that roadmap, those requirements, are visible to all the other components down the line.
Okay. And they mentioned technologies it's based on.
Yeah, built on Open Cluster Management, OCM. And they're planning future integrations with lightweight K8s, distributions like Microshift and Flata.
Why those specifically?
To reach the really resource-starved devices out at the far edge, think tiny sensors, controllers. OCM might be too heavy for them.
Right, makes sense. Okay, so the user defines goals in the CAM via ACM. Who actually looks at the data aspect based on that? Pillar 2.
That would be the metadata manager, MDM. Its whole purpose is to treat data not just as stuff to be moved, but as an integral resource in the orchestration puzzle.
How does it do that? It creates a semantic data catalog. That's pretty academic. What does it mean practically?
Good question. It's more than just a list of files and where they are. A standard list tells you where. A semantic catalog built as a knowledge graph tells you what the data is, how current it is, how sensitive it is, and critically, can you even legally move it to a certain location?
Ah, okay, now I get it. So the MDM is tracking things like data freshness. Is this sensor reading from now or an hour ago?
Exactly. And compliance, like UDPR rules. Can this data leave this country? And portability. How easy is it technically to move this data set and make sure data quality and legal rules impact placement decisions?
So it's not just is the CPU free, it's is the right data available, fresh enough, and legal to use here.
Precisely. That context is key.
And speaking of location and moving things, Pillar 3 must be networking, right?
You got it. Network management and adaptation, NetMA. This is the system's ears for the network. It provides that crucial awareness what's happening on the physical wires, the underlay, and the virtual networks, the overlay.
And they get pretty technical here, don't they? L2SM.
Yeah, they do. L2SM is link layer secure connectivity for microservices. It uses software-defined networking, SDN, to basically create secure private layer 2 tunnels just for pods talking to each other within the same cluster.
Yeah.
Like a dedicated, secure fast lane.
Okay, secure internal comms.
Oh.
And the monitoring, the level of detail seemed impressive. Standard stuff like jitter, link failures via NSM, network state monitoring. But the one that jumped out was link energy consumption.
That one is interesting, isn't it? It's not just measuring power draw, it's a computed metric. Codeco models the energy needed to shift a packet based on its size and the path it takes.
Wow, so you can actually optimize for lower carbon footprint.
Essentially, yes. It lets the system treat energy use as a first-class resource, just like CPU or bandwidth, not just some secondary benefit.
But hang on, calculating the energy cost for every packet, doesn't that generate a massive amount of monitoring traffic itself? Is there a risk of, the monitoring overhead killing performance?
That's a totally valid concern. It's a trade-off. And that's precisely why this raw data doesn't just get dumped onto the scheduler directly.
Oh, okay. Where does it go then?
It feeds into the brain, the cognitive core. Pillar 4, privacy-preserving decentralized learning and context awareness, or PDLC. This is the engine that digests all that complexity and helps make smart, real-time choices.
So PDLC simplifies things.
Exactly. It has two parts. First, context awareness, PDLC-CA. It takes all that raw data compute metrics from K8s, data constraints from MDM, network stats like energy use from NetMA, and it distills it.
Distills it into what?
Into simple aggregated node scores. Remember, the infrastructure manager sets performance profiles, like optimize for greenness or optimize for resilience. PDLC-CA crunches the numbers and gives each potential node a score based on how well it meets that specific goal.
Okay, wait. If you collapse, say, CPU availability, data freshness, and network energy costs into just one number, aren't you losing important details? Is that too much simplification?
It's the classic performance versus granularity trade-off.
Yeah.
If the final scheduler had to chew on every single raw metric, jitter, power cost, data compliance for potentially thousands of nodes across the whole CEI continuum, well, it would grind to a halt. It couldn't make decisions fast enough for real-time needs.
I see. So PDLC does the heavy lifting upfront.
Right. It provides a fast, pre-digested recommendation based on the user's priorities, letting the scheduler act quickly.
And the other part of PDLC? The learning bit.
That's decentralized learning, PDLC-DL. This uses some pretty advanced AI graph neural networks, GNNs, for predicting future resource needs and reinforcement learning, RL agents, to generate those actual node recommendations that get passed along.
Which leads us logically to the component that actually makes the placement decision, Pillar 5.
The final step, scheduling and workload migration, or SWM. This is where the rubber meets the road, where the application actually gets deployed or moved.
And it's different from the standard K8s scheduler.
Yes. K8s usually schedules pod by pod. SWM uses a custom, multi-objective workload placement solver. It thinks about the whole application, potentially a group of interconnected microservices, and uses a graph-based approach to find the best overall placement. It's more flexible than K8's filter and score method.
And it doesn't work in isolation, right? It uses the output from PDLC.
Heavily. It relies directly on those node recommendations, those aggregated scores from PDLC. If the user said prioritize low energy, SWM looks at the nodes PDLC scored highest for greenness.
Okay, so it's using that integrated data compute network awareness, guided by PDLC's intelligence, to make much smarter placement decisions.
That's the idea. And that covers the core architecture they built in the first phase, for managing within a single cluster or a closely managed group.
Right, but the D10 document spends a lot of time looking ahead. Phase 2, M19 to M36. They're tackling federated cluster FC operation.
And this is where things get exponentially more complex. We're talking multiple clusters, potentially across different organizations, different administrative domains. Think scalability, sure, but also fault isolation.
Why is S&C so much harder?
Well, you've got multi-tenancy issues, governance across boundaries, much more volatile edge environments. You need proactive rescheduling, not just reactive. It's like going from managing one building to city planning. It's a whole different scale of problem.
And Codeco has identified 4 big challenges or priorities for this next phase. Let's walk through them. Priority 1 seems fundamental: control plane decentralization.
Yeah, this is a big one. Right now, as we said, ACM leans on open cluster management, which is pretty centralized, a hub and spoke model. That's okay for the cloud, maybe near edge.
But not the far edge.
Probably not. If that central hub connection is flaky or down, your far edge clusters are stranded. So they're seriously debating if they need to break that model, move towards a fully decentralized or maybe a hierarchical control plane.
So keep it simple and centralized, like K8's usually is, or embrace complex decentralization for resilience.
That's the core tension, exactly. It's a philosophical battle almost, driving this next phase. And it ties directly into priority 2, privacy-preserving decentralized AI.
Okay, if you decentralize control, how do these independent clusters learn from each other to make better predictions without sharing sensitive data?
Good question. They're looking at techniques like swarm learning or split neural networks, split NNs, maybe multi-agent reinforcement learning, MARL. The aim is for clusters to share insights, model improvements, maybe gradients, but never the raw local data itself.
So they collaborate to get smarter globally while keeping data sovereign locally.
That's the goal, because PDLC's predictions need local context, but they also benefit from broader, shared knowledge about patterns and resource usage.
Makes sense. Priority 3 is FC semantic abstraction and adaptive networking. Sounds like updating CAM and NetMA for this federated world.
Pretty much. The application model, CAM, and the network manager, NetMA, need rethinking for environments where clusters might belong to different organizations, different trust levels. How do you handle secure networking between clusters?
Right.
They might need to separate how they handle internal cluster traffic that's secure L2SM highway from how they manage traffic between clusters. Maybe something more like how the internet itself routes between different autonomous systems, ASCs.
Interesting. Okay, and the last one, priority 4, FC scheduling, placing workloads across this federation.
Yeah, how do you decide which cluster gets the workload, let alone which node within that cluster? Are they going to build one giant meta-scheduler that oversees everything? Or maybe a hierarchical model? Local schedulers handle placement within their cluster, but they can ask a higher-level scheduler for help if something needs to cross cluster boundaries.
But the goal is still simplicity for the user, right?
Absolutely. From the application developer's point of view, ideally, the whole federation should just look like one massive, seamless pool of resources. The complexity should be hidden.
Wow. Okay, this has been a really fascinating look under the hood. A true deep dive into the engineering needed to connect K8s with the reality of the far edge. So, to recap for everyone listening, Codeco's real power seems to be that systematic integration compute network data awareness driven by AI through those 5 distinct components.
I think that's right. And maybe the most fascinating thing to leave people thinking about is this. The biggest challenge Codeco faces now in this federated phase is that core conflict. K8s has always thrived on a relatively centralized control plane. It's simple, it's robust. But the true promise of the far edge seemed to demand a highly decentralized, almost self-organizing system for maximum agility and resilience.
Centralized simplicity versus decentralized necessity.
Exactly. Figuring out where to draw that line, how much decentralization they can handle while maintaining manageability and security. That's the defining question for the next stage of this project, and maybe for the future of edge orchestration overall.